Hello differential equation students. So in this video we'll take a look at how to solve some very basic differential equation using Laplace transforms, right? Let's see how to solve an IVP using the Laplace transform. So to do that, let's learn some basics of how does the Laplace transforms works with derivatives. So if you have a function f of t, you don't know what that function is, right? And if you want to find the Laplace of the f prime of t without actually having to compute the derivative, right? If you know the Laplace transform of the function, you don't have to know the function. If you know the Laplace transform of the function, right? And if you want to find the Laplace of the derivative, the formula is you multiply s with the Laplace of the function, and then you subtract the initial value, the f of 0, then whatever that you get is actually the Laplace of the derivative. What do I mean by that? Suppose if I ask you the following question, right? So suppose let's just say I have this function f of t is equal to sine t, right? So what is the Laplace of the derivative of the sine t, right? What would that be? You all know the Laplace transform of this one is 1 over s squared plus 1. You all know that, right? So if I use this formula right here, this tells me that I'm going to multiply s with the 1 over s squared plus 1. Then I'm going to subtract f of 0, right? In this case, what is f of 0? As you see in here, if that is f of t, f of 0 would be sine 0, which you all know which is 0, right? So that's a 0 over there. So if you simplify, this is going to be s over s squared plus 1, right? And that's it. And so what is the derivative of the sine, by the way? It's a cosine. So now what you have here is Laplace of cosine t. So because the sine t, cosine t is the derivative of sine t, right? And you can do that. That's what we mean by, that's what that formula says. The good news here is you don't have to know the function, right? Or you don't have to compute the derivative. You can compute the Laplace transforms as long as you know the Laplace transform of the function. We can compute it, and as long as you know the initial value, then we can find the Laplace transform of the derivative. By the same token, Laplace of f double prime of t, second derivative is s squared times the cap f of s, which is the Laplace of the original function f, minus s times f of 0 and minus f prime of 0. For example, by the same token, what is the Laplace of sine second derivative, right? Sine t, the second derivative of that. If I use the formula just like we had earlier, right? Then we are going to do that. If you use the formula, this is going to be s squared, right? S squared times 1 over s squared plus 1 minus s times f of 0. F of 0 is 0, we know that, right? Minus f prime of 0. What is the f prime? We know that here for this one, the f prime, the derivative, f prime of t, you all know, which is the cosine t, and so therefore cosine of 0, which is equal to 1, right? So I'm going to have minus 1 over there. And now if I simplify this, right, then what I am going to have? I'm going to have s squared over s squared plus 1 minus 1. If I simplify this furthermore, you're going to have s squared plus 1, and the numerator would be s squared minus s squared minus 1. S squared and s squared gets cancelled, and what you have here is negative 1 over s squared plus 1. And by the way, what is the second derivative of the sine? You all know the second derivative of sine is, sine, the first derivative is cosine, and the second derivative is negative sine t. You all know that, right? So that's how, as you know, right? So that's how, so as you see here, then Laplace of second derivative of sine is negative sine t, right? Which is basically negative 1 over s squared plus 1, right? So we can get that. And again, the idea is, without actually, these are very simple examples, but there are some functions where it's it's very hard to find the derivative and very hard to find the second derivative. Again, you might not even know the function sometimes, but here it gives you an idea, it gives you a way, a process to find the Laplace of the second derivative, right? And by the way, there's a formula for the third derivative. The good news is there's a nice pattern over here, and we can extend to the nth derivative, and the nth derivative is, the Laplace of the nth derivative is s to the n times f of s minus s to the n minus 1 f of 0 minus s to the n minus 1 f prime of 0 dot 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 dot, all are negative, n minus 1th derivative at 0, right? So these are all constants, and then this is the function part over there, and we can do that, right? Now let me show you how do you solve, right? Let me show you how do you solve a very simple initial value problem using the Laplace transform. Now again, as I said earlier, the idea of solving this is that this three kind of a cycle, right? So what we are going to do, as you see there, first we are going to transform the differential equation from y of t into an algebraic equation cap y of s, and then we are going to have algebraic equation. We're going to solve the algebraic equation, and then we're going to do the Laplace inverse to do the to find the solution back there. And when you do the Laplace inverse, that's where you may have to use a lot of partial fractions, right? So be mindful of that when you work with them, and then you eventually will have a solution to this differential equation. Let me give you a very simple differential equation and show you how these things work, right? Let's take a look at this differential equation, which is y prime plus 3y is equal to 0. Again, easily you can use the M&M methods, right? Characteristic equation and to find that. But the idea is to implement the Laplace transform in solving this, right? So the step one, as I said earlier, we are going to apply the Laplace transform, right? We are going to apply the Laplace transform. From future, I'm going to say LT. If I do that, then what's going to happen is I'm going to have a L of y prime as a function of t plus 3y as a function of t. Let me write it down for you for the first step, equals Laplace of 0. And by the way, Laplace of 0 is 0 because it's linear. It's a linear operator. Laplace of 0 is a 0 there, right? Now, because of these wonderful rules, the inverse, right, the derivative, Laplace of the derivatives, right? What I can rewrite this as, if you first of all let me apply the linearity property, this will be the Laplace of y prime, and this will be 3 times the Laplace of y, which is equal to 0, by the way, right? Now, because of the property that we had and the notation that we said, this is the Laplace of this would be s times the cap y as a function of s. I'm just going to write it down, but don't get confused. This is y as a function of x. That's what I mean by that, not y times s. That parenthesis is not a multiplication, right? And minus y of 0, because I don't know what that is, plus 3 times the cap y as a function of s is equal to 0. Let me make my life easy. Let me give you an initial condition. I'll just say my initial condition is y of 0 is equal to 1, right? It's an initial problem. I'm supposed to have an initial condition, right? All right, so then what happens? Now then I can replace this. Then I can replace this by 1. So let me do that, right? And now what I'm going to do, so now I have a differential equation. I have a differential equation in terms of y of t. I use the Laplace transform. Now I have an algebraic function y of s. That's what I have, right? I have an algebraic function for the function cap y of s. What is the next step? We're going to solve for this y of s, right? And I see there's a y of s in here, there's a y of s over there. If I solve it, ladies and gentlemen, so here's my second step already, right? I'm already here. I'm going to solve for y of s, right? That's my next step. And when I do that, you agree that if I do the y of s, right, to make my life easy, I'm going to keep this on the other side so that you can see it better. So I have s in here and I have a plus 3 over there, right? and minus 1, and I'm going to move this minus 1 on the other side. It's going to become a plus 1 over there, right? Now I have yfs. It's still not simplified. Let me simplify this. If I simplify this, ladies and gentlemen, you would agree with me that this is going to go down over there as 1 over of that, right? So let me do that. Then this is going to become yfs is going to be 1 over s plus 3, right? The next step, so we are right here. Now we have, again, it's algebra, it's easy. From the algebraic equation, we have a solution cap yfs. That's all we have. We have a solution cap yfs in here, right? Now, what's the next step? Next step is to use the Laplace inverse transform and then find the solution y of t. So let's do that. If I do that, then this is going to be, I'm going to say apply Laplace inverse transform, right? Lit, right? Let's lit it up, right? If I do this, then the left hand side is going to be Laplace inverse of cap yfs. As I said, that's what we use the cap for, the Laplace function, Laplace transform the function. And the right hand side is going to be Laplace inverse of 1 over s plus 3. As you know, the Laplace inverse of the cap yfs would be a small y of t. The Laplace inverse of 1 over s plus 3 by the formula is going to be e to the negative 3t. So the solution here, ladies and gentlemen, the solution here to the given initial value problem is y of t is equal to e to the negative 3t. Again, this is a very simple problem. The idea is to how do we apply the Laplace transform in here. So the step 1 is to, given a differential equation, apply the Laplace transform as your step 1. Then you're going to have an algebraic equation in terms of the whatever the variable that you're dealing with, and then you're going to solve it. Once you solve it, then you do the Laplace inverse. Once you do the Laplace inverse, then then you solve for y of t. Sometimes you may also have an equation. Then in this case, it's much easier. Sometimes you may have an equation, then you would have to work with it and solve it over there. Let me do another simple, another nice and simple non-homogeneous problem, and then let's see how do we work with this. Let's take a look at this one. Very similar problem, so let me not change too much things in here. Let's try to solve y prime plus 3y is equal to e to the t, and here is also I'm going to say y of 0 is equal to 1. I'm going to say y of 0 is equal to 1 here as well. Right, let's see how do we solve this one. The process is very simple, right? So the step 1 is applying the Laplace. I'm going to say, let me apply the Laplace transform. When I do that, the left hand side is going to be Laplace of y prime plus 3y. The right hand side is going to be Laplace of e to the t, and using the linearity, this is going to be Laplace of y prime plus 3 times the Laplace of y, which is equal to 1 over s minus 1. And now if I rewrite this one, if I apply the derivative formula for the Laplace, this is going to be s times the cap y. Now I'm going to say y of s. You all know what do I mean by that, right? Minus y of 0 plus 3 times the cap y of s, but I'm just simply going to write cap y, which is going to be 1 over s minus 1. Now my goal is to solve for the cap y, or cap y of s, which if I do that, ladies and gentlemen, by the way, what is y of 0? Y of 0 is equal to 1. So this is the y of 0. This is the y of 0, right? Let me replace that. So if you replace this y of 0, which is going to be 1 right there. And if I simplify this, you would agree with me that I am going to have s plus 3 times the cap y of s, which I'm going to simply write y, which would be 1 plus 1 over s minus 1. On simplification, you would agree that this would be s over s minus 1. Right, this will be s over s minus 1. And so therefore, now we have the solution. Now we're going to solve for y. Now we have the solution cap y in terms of s, right? Algebraic equation. The step 2, what we are going to do is solve for cap y. When I do that, you would agree that my cap y would be simply s over s minus 1 times the s plus 3, right? And now next step is to find the Laplace inverse, right? We're going to do the Laplace inverse. So I'm going to apply LIT, Laplace inverse transform. When I do that, this is going to be Laplace inverse of the cap y as a function of s is equal to Laplace inverse of s over s minus 1 times s plus 3. And here's where I would have to use the partial fractions, right? So let's see how do we do that. And the left hand side is very simple. This is simply, the left hand side is simply y of t. That doesn't change much, right? But the right hand side is, I'm going to use the partial fractions, and again I'll let you do the partial fractions on your own. If I do the partial fraction, what I'm going to get is the following. I would have Laplace inverse of, if you do the again partial fractions, I'm going to have 1 over 4 as my constant a over times 1 over s minus 1 plus 3 over 4 as my constant times 1 over s plus 3. And if I simplify that, ladies and gentlemen, then I am going to have 1 over, if I do the Laplace inverse, there's going to be 1 over 4 of Laplace inverse of s minus 1, which is e to the t, and 3 over 4 times the Laplace inverse of 1 over s plus 3, which is e to the negative 3t. And so therefore your solution, you can say y of t is equal to 1 over 4 e to the t plus 3 over 4 e to the negative 3t. And that's how you would solve these differential equation. This is not a homogeneous problem. Differential equation. In this case, it's not homogeneous differential equations. There are constant coefficients, right? And we can solve them using this. Again, process is very simple, right? Apply the Laplace differential equation in terms of y of t. Apply the Laplace, and get the algebraic equation y of s. And then solve the y for a y of s, and then do the Laplace inverse. Oftentimes the Laplace inverse is the sometimes challenging part, but once you get used to it, if you practice enough, then you should be able to solve all of these things nicely. And I will stop it right here. So in the next sections, we'll take a look at in next set of videos, we'll take a look at how do we solve very interesting and challenging problems with a differential equation, not only differential equations, also what we call integral differential equations using Laplace transforms.